I'll be talking, well, as you can see, about, yes. Today I'll be talking about work that I've done in collaboration with various people, some of whom are present here and some of whom are not. And it's, well, say an overview of results that I've gotten in the last 6 or 7 years or so. I've titled Diffeomorphisms, Observables and Noncommutativity. And I'll tell you that diffeomorphisms are actually a problem if one wants to connect the results that one can compute with observations, but that these can be cured. So this is will be the main message of my talk. I have prepared slides for, say, 4 sections. So first, I'll tell you about perturbative gravity, and I put the quantum in parentheses because everything I say also applies to classical gravity. Then I'll tell you about the important subclass of observables, namely those that one can find at linear order. Situation there is a bit special. Later on, of course, one wants to go further in perturbation theory, so also look at higher orders. And then finally, I tell you about very recent work together with Albert Much and Kyriakos on non-commutative coordinates that also came out of this. And of course, I'll conclude. Please feel free to interrupt me at any time if you have questions. So I think there will be enough time. Okay, first section, perturbative gravity. Of course, you probably all know physicists like to describe things by actions. So what we do is we take as our full action the action for gravity. It's just the usual Einstein-Hilbert action. So it's some prefactor, which depends on Newton's constant. There's the Ricci scalar of the Levi-Civita connection that is associated to the metric G. There's a cosmological constant term, which you can set to 0 if you like, and then you integrate over the whole manifold. And then you can choose some matter action, which I won't specify here in detail. That then depends on what theory you'll be studying. Yes, I've written, as said, R is the Ricci scalar. And if you like to work in local charts, as all the physicists do, then the volume measure is just the square root of y is the determinant of the metric. So we have Lorentzian signature times d4x. As all students know, this is an action, so you can compute Euler-Lagrange equations. And well, it's a computation, it takes some time, but after the dust settles, what you get is that on the left-hand side, so that comes from the variation of the Einstein-Hilbert action, you get the Einstein tensor, which is just the Ricci tensor of that Levi-Civita connection, minus 1/2 Ricci scalar times the metric. I realized I forgot to put the cosmological constant here, so you have to add plus lambda g mu nu, if you have it. And on the right-hand side, you get the stress tensor of the matter, or also called energy momentum tensor. And this is just a variation of the matter action. So I've written here the formula. Depending on your convention, there might be a minus sign, or maybe not the factor of 2, but this is what I'm using. And then once you have this, you also realize that there is a symmetry of this action, namely diffeomorphisms. And for physicists, diffeomorphisms are nothing else but changes of coordinates. So instead of your coordinates x mu that you use to describe your manifold in a local chart, you change to x mu minus some function psi mu, which can depend on coordinates x. And as a physicist, well, I always like to work to first order in psi, and this is what is called infinitesimal diffeo. So whenever I say infinitesimal, or whenever a physicist says infinitesimal, it just means to first order in psi, to ignore all higher order terms. And that means the change of coordinates under such an infinitesimal diffeo just given by minus psi mu. Again, the sign is convention. Then you can look at what this change of coordinates induces on fields, on tensor fields on your manifold. And it's very easy computation to see or to show that the change of a tensor field, so some t mu nu, again, some abstract indices can be arbitrary tensor field, is just a Lie derivative with respect to that vector field C. And again, something that a student can already compute, the action itself is invariant. So that means that if you compute the variation of S, so of the total action, gravity plus matter, you get 0, assuming that your function psi, or your vector field psi, vanishes on the boundary. Sorry? Okay, I thought I heard a question, but So assuming that xi vanishes on the boundary, or if you have a manifold with no boundary but some infinite ends and vanishes at infinity, then you get that the action is invariant. So that means that diffeomorphisms are symmetries of gravity, which should be well known, I think, to anyone working in differential geometry. If you have a boundary, you need to be a bit more general and add boundary action, which in this case is Gibbons-Hawking-York boundary action. But for the purposes of this talk, I will always work, say, on a manifold without boundary or asymptotically flat. So then this won't matter. Okay. What does this entail for the important field, namely the metric? So change of the metric, as I said, every tensor field changes with the Lie derivative. If you look at it, what this is in local coordinates, it's just this expression. And then these terms one can assemble to just give the covariant derivative of your vector field xi, symmetrized in mu and u. And nabla is the covariant derivative of the Levi-Civita connection, as it well known. Okay, a symmetry, this is very nice. If you hear the word symmetry, you should hear the word, you should think about Noether's theorem. You can apply this to this case, but unfortunately it doesn't result in anything useful for the case without a boundary, because you only get boundary terms from Noether's theorem in this case. And this is a telltale of a local symmetry. And I mean, as I said, xi is a vector field on your manifold, so it can depend on the point. So it is a local symmetry, so everything is consistent. So unfortunately, in this case, we cannot rely on Noether's theorem to tell us anything useful if we don't care about boundary terms. However, what we get is we get that the Euler-Lagrange equations that we just derived are covariant. So you look at a metric, you take your original metric G, you add the Lie derivative with respect to some xi, you get some metric G prime. The same for all the matter fields. Sorry, this should be a phi prime here. So then if the Euler-Lagrange equations, the Einstein equations, are fulfilled for your metric G and phi, they also will be fulfilled for G prime and phi prime. Again, it's an easy computation. And then, of course, the question arises, well, so what is actually the physical thing? What is the right metric? Is it G or is it G prime? What is the right matter field? Is it phi or is it phi prime? And what can be actually measured? What can be observed? What is the right thing that we can tell to some experimental physicist? Please measure what this is and tell us what you get. And well, as one clearly sees, any local field cannot be measured. The metric is some local field. It's defined at each point in space-time. And it changes under a diffeomorphism, so it cannot be observed. Only non-local things are physical, can be observed. And one prominent example that people in differential geometry, of course, also know is the so-called ADM mass. So it's a quantity that is defined for some asymptotically flat manifold in asymptotically Cartesian coordinates. It's this formula here. You can find it in many textbooks. What do? You take your metric in these asymptotically Cartesian coordinates. You take a certain derivative. You integrate this over a ball at infinity. So there is a big surface at infinity with some surface element dsi. Kr is the ball of radius r. So integrate this over the boundary of that. And then you take the limit of r going to infinity. So essentially, you're integrating first derivatives of the metric at infinity. So it's a boundary term. And this is a well-defined thing. And it's used, for example, in the Schön-Yau positive mass theorem. So this is something that is physical quantity. But of course, you might think, well, there should be more, right? Because we are living here in a world on Earth. This is not something that is at infinity, far away at the universe. We have something local here that we can measure.
Markus, I think there's a question of Nikolaos Kalogeropoulos.
Okay, Markus, sorry to interrupt you. Do you happen to know whether there is any recent work on any manifestly covariant expression for the ADM mass? Because this is clearly non-manifestly covariant. I mean, I know they were looking for it for a while, but I don't know whether they came up with anything. Do you happen to know anything about this?
No, sorry, this I don't know. Yes,
okay, all right, good enough, thank you.
Sorry about that.
No, it's fine.
So I'm focused more on things that can be made to be a bit more local than that. And then for this, there are covariant expressions. I will show you later. But for the ADM mass, I don't know. I'm sorry.
Can I also ask something else? This may be certainly outside you know, during the last 20, 30 years, people have been looking into what is called topological field theories, right? Which also do not have any degrees of freedom. Does this statement that you make that there are no local fields, does it imply that gravity is a topological field theory in 4 dimensions, 3+1 dimensions always?
No, so I didn't say that there are no local fields. I say local fields are not physical. So there are local fields. The metric is a local field, and it has the 2 polarizations of gravitational waves, so 2 dynamic degrees of freedom. But those ones locally at the point are not physical. This is what I'm claiming.
Okay.
So gravity is not a topological field theory in 4 dimensions. But if you actually want to extract observable quantities, you have to think a bit harder than just looking at local fields.
Okay, yeah.
This is what I've got. Okay, great. So, and now we come a bit more to say my work, which is perturbation theory. If you want to think about these questions in full generality, so without invoking some kind of perturbation theory, it is very hard. And perturbation theory is a useful approach in many cases, so also in this case. What do? You take your full metric G, you decompose it into a background metric G0, and a small perturbation H, so this is say first order. I always will write the perturbation order in a parenthesis on a tensor, on a quantity. And of course, there also needs to be a perturbation parameter, which in this case I call kappa, which is basically the square root of Newton's constant in some appropriate units, and it's proportional to the Planck length. So it's a very small parameter, so one should hope that this is a very good perturbation theory in a sense. Yeah? The linear approximation is already a very good approximation, and to obtain the equations for that, you take the gravitational action to second order, because then the equations of motion that you will get will be first order in H, and the matter action to linear order, because then you will only get the matter contribution in the stress tensor. And this, in fact, this linear approximation is sufficient in the quantum theory if you want to compare with experiments. So we know we have experimental data from measurements of the cosmic microwave background, which basically gives us something which is called a power spectrum. I won't go into much detail that, but there is a nice connection. And this linear approximation, what we get out of that, is sufficient for a comparison of that data with the prediction of the theory that you get by quantizing this H at linear order. And they agree. So this is all very nice. So what we have to do in addition is you consider a fixed background. As I said, there's a background metric G nu. For example, this could be flat space, Minkowski metric, or it could be a Friedmann-Lemaitre-Robertson-Walker metric for cosmology. And since you're doing perturbation theory, say your background is really fixed. So there I don't change my coordinates. I keep that, Minkowski and Cartesian coordinates, for example. And I make my diffeomorphisms also small. So I add an additional parameter kappa in front of my vector field psi. So now my diffeomorphisms are not only infinitesimal, so first order, but also small, because there's a kappa. And those 2 things are not the same. And what you see if you plug this into the formula for the diffeomorphisms, for the change of tensors, is that they now connect different orders. So the change of a tensor at order k will be the Lie derivative of the same quantity at order k minus 1, just because there's an additional kappa here in front of the psi. And one thing that is a classical result in perturbation theory, in gravity theories or differential geometry, is called Stewart-Walker lemma. Yes.
Oh, hello.
Hello. Do you have a question?
Yes. What is your name?
Markus.
What section is it? Is it calculus? Is it which class?
It's not a class. It's a seminar.
Oh.
Okay. No problem.
I'm sorry, I think Dr. Adon was talking to a student in his office, but I forgot to mute him. My apologies.
No worries.
My apologies. He was not referring to you, of course.
Okay.
My apologies. Yes.
No problem. So as I said, a classical result in differential geometry or perturbation theory is the Stewart-Walker lemma. I think it's from the 70s or 80s maybe. Clearly, if the Lie derivative of tk minus 1 is 0, which means that tk minus 1 could be a constant or a linear combination of deltas with constant coefficients, then this is 0. So then the tensor at order k does not change under small diffeomorphism. But the Stewart-Walker lemma tells you that also the reverse is true. So if this quantity does not change at order k under diffeomorphisms, then the quantity at order k minus 1 is a linear combination of deltas with constant coefficients. So, okay, this is all I want to tell you about gravity, diffeomorphisms, and perturbations. So now the question is, what can we use, or can we use this to construct observables, to construct things which don't vary, which have delta tk equals 0. So first, let's look at the case of linear order, which is an important subcase, as I said. So at linear order, the Stewart-Walker lemma, as we just seen, it shows you how to construct local observables at first order. Namely, you just take the expansion of any tensor that vanishes on the background. And then, of course, Stewart-Walker lemma tells you, well, then at first order, this quantity will be invariant. So, well, it's always nice to look at examples. Example, very easy example. We take flat space as a background, Minkowski. So it's a flat metric. G0 is just eta. And the Riemann tensor, the curvature tensor of eta vanishes. So that means that the linearized Riemann tensor, the expansion of R at first order, will be an invariant quantity. Delta psi of R1 is the derivative of R0, which vanishes, so this is 0. And one can also see this very nicely explicitly. So I've written down here the formula for the first order expansion of the Riemann tensor. It's just some anti-symmetrized second derivatives of the metric perturbation H. Yeah, it's anti-symmetric in rho and sigma and nu, pairwise. And change of the metric perturbation H. So it's the specialization of the formula that we had, nabla mu psi nu symmetrized in the flat metric. So it's just d mu xi nu plus d mu xi mu plus some higher order terms, which we can ignore at linear order. And then if you plug this in here, you see that the derivatives again cancel pairwise. So for example, take this term here. There will be one d nu psi sigma coming from here, from this term, d nu psi sigma. So we have d mu, d nu, d rho psi sigma. And this will cancel with another derivative, I think, from this term. Yes. So from here, there's a d nu, d rho, d mu psi sigma with a minus sign. So this just cancels this one. And then these terms cancel pairwise. So we can see really explicitly that this is some invariant quantity. It's very nice. And this idea, of course, can be generalized. So in general, what you have to use is a so-called ideal characterization of your background space-time. I don't know if you know this. An ideal characterization, that's a set of tensors that vanish if and only if space-time that you're looking at is locally isometric to some reference space-time. So this is something that has been done by people in Spain, not in Barcelona, but in Valencia for some time, and then recently by another collaborator of mine, Igor Hafkin from Prague. And so, the classical result is, of course, the ideal characterization of Minkowski is the Riemann curvature tensor. The classical result of differential geometry, geometric is locally isometric to the flat metric, if and only if the curvature tensor vanishes. So this is a very simple example, and this can now be generalized. So for example, take de Sitter space or anti-de Sitter space. So that's the maximally symmetric background space with constant scalar curvature. So the ideal set is the Riemann curvature tensor minus a constant times this combination of metrics. For some positive constant, then it's the Sitter space, or a negative constant, then it's anti-de Sitter space. Yeah, so what do I mean? Take some space-time, compute this quantity. If it vanishes, then your space-time is de Sitter, or anti-de Sitter, depending on the sign of your constant. So that just tells you that anti-de Sitter or de Sitter space is a maximally symmetric space. The Riemann tensor is equal to this combination of metrics. That's it. It's a very simple idea. And then from this, by the same procedure as before, you take the linearized version of that, and you get a first order observable. So you take the linearized version of your Riemann tensor. K is a constant, that doesn't change. And then you linearize this. So this gives the background metric times the linear perturbation H plus H background metric minus the other way around. And if you think a bit harder or really compute what this is just the linearized expression of the Riemann curvature tensor with two upstairs and two downstairs indices. So twice covariant, twice contravariant, and then the indices lowered with the background metric. And you can check that this is invariant. Why is this invariant? Because with two indices upstairs and two indices downstairs, the background Riemann tensor is a combination of deltas. You see, if the first and the third index are up, then this is a delta mu rho, delta nu sigma, minus the other way around. So then the Lie derivative vanishes. And as Stuart Walker lemma tells you, the first order thing is an invariant quantity. So it's all very consistent. There's another example. One can look at FLRW metrics or spacetimes. As I said, they're important for cosmology. In this case, the background metric is a conformally flat metric. So it's a squared times the flat metric eta in Cartesian coordinates, let's say. A is the so-called scale factor that depends on time. That's also called eta, confusingly, but okay, so is life. And this is the solution of the Einstein equations with the stress tensor of a scalar field, phi, which is called the inflaton. And this metric, so you can write down an ideal set, so a set of tensors that vanish exactly for this spacetime. I haven't given you the expression. It's in that paper. So this is of this guy, Igor Chavkin from Prague, together with an Italian collaborator and a master student, a very good master student. It's a horrible expression. It takes half a page to just write down. So I didn't want to give you the expression. But it's very nice. So I mean, it's very clear conceptually. Just the expressions get very long. And then we can use this, again, to construct observables at first order, by the same procedure as before. What do you get? Well, you get the linearized Weil tensor. This is very clear. Your background metric is conformally flat. That means the background Weil tensor vanishes, so the first order is invariant. That's a very, very clear thing. What else do you get? You get the linearized Einstein equation. So you write down your Einstein equation, Einstein tensor equals stress tensor. You linearize that around the background. On the background, it vanishes, so the first order thing is some gauge invariant stuff. You can write it down, it's a long expression. So these are the two obvious first order observables. And then there's a third one, which is a tensor C mu nu, which is a horrible thing, which took a year to construct. And this comes from some of the other tensors in this ideal characterization here. It is something which is constructed from the extrinsic curvature of constant inflaton hypersurfaces. So you look at them in the perturbed spacetime. And there is some relation between the Hubble rate, which is the derivative of this scale factor, and the potential of the scalar field that enters in the Einstein equations. So I didn't give you the explicit expression here. Again, it's some long quantity. It's in that paper if you want to have a look at it. And one can really check that these things are invariant at first order. So these all are some nice physical quantities. And the nice thing is about this whole ideal construction is that you get a complete set of local observables in this case. So this is the only exception to what I said before, that there are no local observables in gravity. At first order, if you restrict to first order, you can get local observables, exactly from this ideal construction. But that only works at first order. It has also been used for black holes, so that's also a big field of study. It's also seen much activity in recent years. There are many papers. I don't want to give you all of them, but if you're interested, I can send you some. Any more questions at that point?
Yes, Markus.
Yes.
If you consider, let's say, the Schwarzschild solution, how consider the perturbation within a linear order, right, of Schwarzschild? How do these local observables look like to develop some feeling about it? Do you get back the mass? But apart from the mass, do you also get, how do they look like? I mean,
yes,
you don't have to write the equations, just give basically some intuition behind it if possible.
So what you get is you get some combinations of components of the Weil tensor, basically.
Okay. But is there a geometric interpretation of these things? Because Schwarzschild is completely geometric, right? It is T mu nu is 0, basically. So do you guys have any idea whether it means something geometrically or?
Yeah, so the interpretation, so the observables at first order would be some wave-like perturbations that you can add on top of that background.
Very good, thank you.
So I mean, for Schwarzschild, this sort of was known. So there are these constructions from the 80s, I also think.
But still,
I forgot the name. But the point is that so with this ideal construction, one can now really show that this is a complete set. So there's nothing more. With this one can characterize all the things, but you get basically back the same things. For Kerr, so for rotating black hole, there's a recent paper, I think from also 2018, or 19 maybe, which shows that there are 2 more observables that were not considered before.
Yeah,
which I don't know the exact interpretation, but if you want, I can send you the paper later. Okay. Yeah, and of course, and then what one can obviously also do is one can take non-local observables. Yeah, so ideal construction with local things, but of course one can also look at non-local observables. It's not an obstruction. For example, the well-known Bardeen variables in cosmological spacetimes, they are non-local. There's a construction, I don't want to write down the details. And then the question is, what can you get with these observables? Now that we have them, one is to compute some certain things. And the very nice thing, a very nice result in linear order, are one-loop quantum corrections to the Newtonian potential. So you take some free particle in a flat space background, the sun, for example, just sitting there, or some body. And now you assume that there are some matter fields, like quantum fields, fluctuating around, and you check how does this change the gravitational attraction of that particle. How does this change the Newtonian potential? Yeah, so it's a sort of vacuum polarization effect of these quantum fluctuations. So what one has to do is one has to find something which I call, say, H00 inv. So it's an invariant observable which is constructed non-locally, analogous to the Bardeen variables, of the 0, component of the metric perturbation. And then the Newtonian potential is just 1/2 the expectation value of that. Like in classical GR, if you take the non-relativistic limit for a single body, it's a standard exercise in GR, I think, general relativity, the Newtonian potential you get from 1/2 of the time component of the metric in that case. And one can compute this. So this is the result that one gets. The classical result, of course, is just minus a gm over r. G is Newton's constant, m is if the mass of the particle, r is the distance, and then one gets this correction factor at first order, at linear order. So there's the Planck length over r squared. So it's a very, very tiny correction, impossible to measure experimentally, of course, but it's there. It's a prediction of the theory at linear order. And the coefficient is, well, a strange numerical factor, 45 pi, and it depends on the number of matter fields that you have. Yeah, so there's n0, it's the number of particles of spin 0. So for example, the Higgs particle, that scalar particle, n1/2 is the number of fermions, so like the electron or the neutrino, and n1 is the number of vector fields, like electromagnetic potential. And xi here in this case is some non-minimal coupling, so that one can also compute. And then there might be higher orders, but this is something that you can get at linear order. This was already known by other methods, but it's very nice that one can also get it using these observables in some nice effective action method. One can generalize this, in fact, to some de Sitter background, or also to spinning particles. So here I consider really a body at rest. So this gets its potential corrected. But of course, one can think about a rotating body like Earth that rotates around itself. Then one gets corrections to the gravitomagnetic potentials. So that will be the 0I components of the invariant metric perturbation. It's in these papers. Nice computation, nice results. These are the things that one can now do at linear order. And now you would think, well, here I only put spin 0, 1/2, and 1, so only scalar fields, fermions, and vector fields. What about spin 2? What about graviton loop corrections? If you quantize gravity, if you take background plus fluctuations, then also gravitons should fluctuate around and change this gravitational attraction, give some quantum effect, but that is higher order. That would not be an effect at linear order. So we have to go to higher orders. Observables at higher orders. Okay, first observation that we make. Well, clearly, at first order, what we have is not trivial. So at second order, we will get something which is not gauge invariant, just by the same Stewart-Walker lemma as before. So clearly, beyond linear order, there cannot be any local observables. Anything must be non-local. And people have thought about this a long time. I mean, starting from the very early days of GR. And the solution is, in fact, well, quite simple, I would say, once you actually know it. So with hindsight, it's always simple, of course. So let me explain how can you solve this problem, and then tell you why this is useful. So I give a recipe for the solution. I take 4 fields, x mu, which I call x mu. They depend on the metric. They might depend on matter fields, scalar fields, whatever you have in your theory. And they should be such that under diffeomorphism, they transform as a scalar field. So I've written you down here, transformation of a scalar field. It's just the xi rho d rho. So even though they have an index mu, I put this index in brackets because it's not a vector field. They're really 4 scalars. So they should transform as a scalar. And I also say on the background space-time, they have some background value. Okay. X mu 0. Now, this quantity I can expand in perturbation theory. I have some x mu 0 plus kappa x mu 1 plus kappa squared x mu 2 and so on and so forth. I invert this whole expansion. So I write x0 as a functional of x and the higher order corrections. So one can do this in perturbation theory. It's invertible as a formal series. I'm not saying anything about convergence. It's invertible as a formal series. And then, of course, if x transforms as a scalar, then this inversion will transform inversely to a scalar. And the invariant observable, which I call calligraphic A of chi, this is now a composition of these things. So I take my field A, which might be a metric, which might be a stress tensor, any tensor field, at the position x0, and I hold the x fixed. So in, say, differential geometry terms, I compose A with the inverse of x and x0. And this construction is, well, this goes under the name of relational observables. So x mu is called configuration-dependent coordinates. There are 4 fields, 4 scalar fields. So this is enough to be a coordinate. It's called configuration-dependent because it depends on your metric, on your field phi, so the configuration of fields. And this calligraphic A of chi, that's the value of A at that point where the chi is equal to x, to capital X, by this construction. And then evaluating it at x0, what you do is you interpret this calligraphic A as a field on the background spacetime. So this is the construction. I mean, it looks, if you first look at it, it looks a bit strange, but once you do, say, a first order computation, it becomes really clear and obvious. And I will show you later how the first order things look like. And what you can see from this thing is that x0 is the background that's supposed to be fixed. We don't change that. That transforms inversely to a scalar. And if, say, A is a scalar and you compose, then this should not transform at all under difference. This is exactly what this construction does. And of course, if A is, say, a tensor, then here you also get the Jacobian from a coordinate transformation and everything still works out. So this is something that with various collaborators I've been working on the last 4 or 5 years as relational observables. This is the general construction. And now the question is, how on earth do you find these 4 fields X? We need 4 scalar fields X. How can you find them? Well, if you're in a generic spacetime, so very inhomogeneous, a lot of curvature, whatever, you can just use curvature scalars. Yeah, Riemann tensor squared, Ricci scalar squared, whatever, anything you like, on a generic spacetime. So it must be generic enough such that the value of these scalars differentiate points. Yeah? It must change from one point to the other. So you know that the different points have different values because these should be coordinates in the end. So they should change. If you're not in a generic situation, if you are, say, in flat space, Minkowski, what you could do is you could add the scalar fields by hand. Yeah? Just add some more scalar fields into your theory. A famous example is the so-called Braun-Pucher-Stast. This is a very nice thing. But of course, if you add something to your theory, you change the whole dynamics. You change the Euler-Lagrange equations, you add something to the stress tensor. This has been very, very nicely elaborated in this paper by people from Erlangen, so working on loop quantum gravity. So maybe this is also not what you want to do. And then you think that, well, we want to do cosmology. In cosmology, at least we have one scalar field. Yeah, I told you before, there's the inflaton that generates dynamics, that's a scalar field, but we need 4. So there's a problem. And if you look at Minkowski or the sitter, there's no scalar field at all. It's just pure metric. Or even in Schwarzschild, there's no scalar field. And this is something that people have been really thinking hard about. And the first complete solution in cosmology, so for some FLW metric, was in this paper by, it's a collaboration of mathematical physicists from York in England and a guy from Leipzig and some people from Italy. like 6 years ago. We only call it the many people paper because there are really many people on that paper. You take your FLRW background, you have one scalar field, the inflaton. That gives you a time coordinate. And then, since the background spatial coordinates, they're harmonic. So FLRW, it's conformally flat, and the constant time surfaces, they're just flat Cartesian. And these coordinates are, of course, harmonic. Laplacian of x, second derivative gives you 0. So what they did is to define the capital X, at least the spatial ones, as harmonic coordinates for the full Laplacian. So you take your hypersurfaces of constant phi in your perturbed metric, you compute the Laplacian on these hypersurfaces, and then you define X as harmonic coordinates in this for this Laplacian. And this can be solved order by order in perturbation theory. I give you the formula later on. It's a bit long, but it's not very important now. And then one can use these coordinates now to construct things. For example, one can compute something which one might call the invariant metric perturbation. So we recall that H itself changes under diffeomorphisms, but with this construction now one can turn it into some invariant quantity. So what you do, you take the full metric G, you do this procedure of the last slide. So you take A compounded with x minus 1, compounded with x0. So that in local coordinates gives you d small x a, so the Jacobian of the coordinate transformation, and then the metric evaluated at small x depending on capital X, so that inversion from before, and you subtract the background metric. And then you compute this order by order in perturbation theory, holding capital X fixed. And the first order result is that you get your metric perturbation back, and there's a correction term. And the correction term is, well, it's a background metric, background covariant derivative of the first order correction to these coordinates. And one can do these computations for, say, these harmonic coordinates and the time coordinate coming from the inflaton. And if you do this nicely, then this result gives you exactly back the Badin variables. So the Badin variables, which are very known, well known in cosmology, they're a special case of this relational construction for specific choice of time coordinate and these harmonic coordinates on the spatial surface. So this was really, I think, the first result for this relational observables for homogeneous backgrounds, for backgrounds where you don't have these scalar fields automatically. And the nice thing is that this construction works to all orders. So you can, this is the first order. It becomes, of course, complicated the higher you go in perturbation theory. But in principle, one can compute this to all orders and crank the machinery and get something that is invariant. And okay, this can be generalized. Of course, the flat space, you can generalize it. One not so nice thing about this construction is that you have to invert the Laplacian. So it's non-local, of course, but it's non-local at a fixed time, so it's also not causal. Some action at a distance, if you want, some influences from spatially separated things. You can amend this construction to make it causal. So to restrict this non-locality to the past light cone. This is something I've been doing with collaborator William Lima, who is listening now. Hi, William. And one can also generalize this to something that people in cosmology have been looking at, which are called geodesic light cone coordinates. Sorry. If you're interested, I can tell you about this a bit at the end if there's time. Also something that I've been doing with William in this very recent paper. And now that we have these observables, one can use them to construct things. And one of the first things that I've been doing, again, together with William, was to compute the correction to the Hubble rate. So the Hubble rate, sorry, H, that's the expansion rate of the universe. Our universe is expanding exponentially. And the Hubble rate is the rate with which this exponential expansion progresses. And of course, if you're on a background spacetime, it has a fixed value, let's say, in de Sitter, for example, or slowly time-dependent value. But there are quantum corrections to that coming from quantum gravity. And now with these invariant observables, one can actually compute them and be sure that the results that one gets do not depend on an arbitrary gauge. So a lot of people have computed these corrections. A lot of people have done it for a long, long time. But everyone chooses some nice gauge, and then you never know whether the effect that you get depends on the gauge or is really physical. So it's hard to compare with observations. But now with these gauge-invariant observables, one can really compute something and know that the result is physical, something that really can be compared directly with observations. Okay, so after this propaganda, let me tell you the results. So recall the background metric is conformally flat, eta is the conformal time, and on the background, the Hubble rate is just the rescaled derivative of the scale factor. So you can also write this as 1/3 of the divergence of a 4 velocity of some observer that is moving at the same speed as the inflaton. So it's just the gradient of this phi. So as you see, it's a divergence of this 4 velocity, so it gives you really an expansion rate. And then with this construction, with these invariant observables, one can look at, for example, at the first correction. So the first correction to the invariant Hubble rate looks like this. Okay, some expression. It depends on the metric perturbation. It depends on the perturbation of your scalar field. And there's some parameter epsilon here that appears, which is the derivative of h, so-called first slow roll parameter, for cosmology. And here, a nice thing is that h1 is local. There's a reason for that. But if you look at, say, second order, it will become non-local again. So again, at first order, you might get something nice and local, but in general, it's not local. Anyway, you can compute this. It's a nice short computation. And then you can compute expectation values. So take some expectation values at one loop, say for various background spacetimes. There is a phase during the expansion of our universe, which is called meta-domination. It has a certain epsilon, 3/2 in that case. And this is the result that you get. So if you're on the background, you just get the h back that you have. It depends on time in a specific way. And then there's a quantum correction, again, proportional to the Planck length, so very small. But there's a log of a here. So a is the scale factor, so the size of our universe that grows. Log a still grows, slowly, but it does. And so you see that the Hubble rate that people can observe actually goes down in time. It's a bit smaller than you would expect from the background. This is what people call screening. It's screened by quantum effects. Look at one-loop quantum effects. So there's a Planck length here. And so this is what people also call secular effects. And so this is something that now, well, numerically, it's very small, so not very nice, but in principle, this could be observed. Yeah, okay, I have some time. So what is the physical idea behind that? Well, the universe expands. So this expansion creates particles from the vacuum, something that people learn in QFT courses, in this case, gravitons. And these gravitons interact. Gravity is attractive, so they attract. So the expansion slows down. This is the mechanism behind that. And this is exactly what we see. So this is, say, the proper mathematical confirmation of this physical idea in that specific case. There's another phase during the expansion of the universe, which is called radiation domination, which is epsilon equal to 2. In this case, there's no one-loop correction. And again, this is very physical because, people, so Soviets, Russians, and US Americans know for a long time that in radiation domination, there is no graviton production. So there's a special case where this physical picture sort of doesn't apply, which is exactly this case. And again, the results fully agree with that. Yeah, so this is it's all very consistent. And then there's a phase in the very early universe, which is called slow roll inflation. There's a very tiny epsilon. And what you get in this case is a correction to that epsilon. So the resulting spacetime is a bit closer to the zeta space than you would expect without these quantum corrections. And there are similar results for a slow roll inflation, which has some change in epsilon. So this was done by William. All very nice. Okay. What else can you do? Well, as I said before, we had this correction to the Newtonian potential. Now we can also look at graviton loop corrections to that. Maybe I don't want to bother you with all the details. So you have to take, now for the matter action, the action for a point particle, some body of some mass. Maybe I don't want to go into all the details because it's getting a bit late. You have to do a large mass expansion because you don't want to look at the fluctuations of the particle, but the fluctuations induced by the gravitons. You get some classical correction that agrees with the Schwarzschild metric, and you get some quantum correction, which is an interesting one. So here I've given you a picture. I hope you can see it. So there's the blue line, which is the classical potential that comes from the expansion of Schwarzschild, the Schwarzschild metric. And then there's a quantum correction which lies slightly below it. Yeah, so in orange here. It's a very, very tiny difference. So what this tells you is that the gravitational force at small distances is strengthened by these quantum corrections. And again, we know it's a physical effect because the observables are gauge invariant. So it's a nice thing. If you actually look at what you get, well, you get two contributions. So one, again, so h bar gn, this is Planck length squared. Again, it's Planck length squared over r squared, very, very tiny. There are two contributions. One comes really from these virtual gravitons fluctuating around. And that in flat space agrees with some other method, which you can use in flat space, so-called inverse scattering method. And there's a second term in this case, which is a remnant of the fluctuations of that particle. So even though we try to suppress them, we can't get rid of them. So it's a small correction. We interpret it as a kind of a Zitterbewegung, which people might know from the classical solutions of the Dirac equation. But another interpretation of the result is that if you look at where this crosses the zero axis, it's since the gravitational force is a bit stronger at small distances, what you get is that is a decrease of the horizon radius of a black hole. You know, if you want to interpret it in that way. So you don't get the classical Schwarzschild radius, which is just 2gm, but a tiny correction to it. It's a tiny bit smaller. So your quantum corrected black hole is a bit smaller than the classical black hole. This is the interpretation. Okay, very nice. And then I think, I'm almost out of time. So let me come to the last part, which is non-commutative coordinates. As we have seen, we need to construct a coordinate system to get these invariant observables. And these coordinates, they depend on the metric, they depend on the matter fields. These do not commute, so also the coordinates don't commute. So out of this construction, out of thinking about how one can construct observable things in quantum gravity, non-commutativity falls out automatically. There's no need to introduce it by hand. And this is work I've been doing with Albert Much and Kyriakos, which should soon appear in Physical Review. So what can you do? It's 4 slides, maybe I don't want to show you all of them, but what we take generalized harmonic coordinates. So you take your full perturbed D'Alembertian and impose that this vanishes. And then the correction that you get at first order looks like that. So in background space-time, you have Cartesian coordinates. Nothing changes. And the first order correction is an integral of some Green's function convolved with a certain combination of derivatives of your metric perturbation. And this is the Green's function of the flat D'Alembertian. So you can, and then the question is, which one do you want to take? Well, we said it should be some causal thing. So in the classical theory, you would take, well, the retarded Green's function. It's a Green's function. And in the quantum theory, maybe you want to take the Feynman propagator. That's the usual thing. One has to think about what really is the right thing, and I will tell you about this in a moment. And the H here, it's a quantum field. It has a non-trivial commutator. So of course, the X, which is a function of H, also has a non-trivial commutator, as I told you. Now, it's a linear theory. So the commutator will be just proportional to the expectation value times the unit. And then one can actually compute this. Yeah? So to compute the commutator of this x1, you just have to compute the expectation value. For this, what do I need? I need a graviton propagator, Feynman gauge, very nice. This is a standard Feynman propagator, scalar one we find in every textbook. It's a standard computation. There's only one small thing that one needs to think at, which is a possible IR divergence. So if I go back to here, you see, you integrate this over the whole space-time, over the whole y. And even if you take, say, the retarded Green's function or the Feynman propagator, so this will be maybe 0 outside of the light cone, you still integrate over the full light cone. So there's an infinite volume, and infinite volumes might give you infrared divergences. So, of course, people have been thought about this in other situations, so there are some nice related papers. There are some people from York, and the solution to resolve this IR divergence and get something finite is to use the informalism, which is also called Schwinger-Keldysh formalism or closed time path formalism. So this is used in say, condensed matter theory a lot. And this informalism computes true expectation values and gives you a way to resolve this IR divergence. So it's explained nicely in these papers exactly how to do that. So what you have to do is basically, instead of just integrating in time forward, so the so-called in-out formalism, where you just compute matrix elements, you add some backwards part. So you compute forward in time and then back. And so basically you have a doubling of fields. Yeah? So instead of just one metric perturbation H, you have two, the plus and the minus one. One is on the forward contour, one on the backward contour. If everything is on the forward contour, you get time-ordered expectation values. If they're all on the backward contour, you get anti-time ordered or Dyson. If they are mixed, you get some Weidmann functions. And that, of course, means that you also have now two sets of non-commutative coordinates, one on the forward contour and one on the backward contour. And you have to put plus and minus green functions to compute these things. So this will be the Feynman propagator, the G++. The G minus minus will be the anti-time order propagator, and these will be Weidmann functions, G plus minus and G minus plus. And in the classical limit, both these time contours coincide. And of course, the coordinates x plus and x minus just give some 1x, and you get from this formalism actually the retarded Green's function. So the informalism is the correct quantum theory generalization of a causal evolution, which is what it was designed to do. And then the IR divergences you can avoid by choosing an adiabatic interacting vacuum. So this is explained in the papers. I don't want to give you many detail. In practice, what you have to do is the initial time you don't go directly to minus infinity, but you add some evolution in, not to minus infinity, but you add some evolution in imaginary time. So plus or minus epsilon, depending on which branch you're on. And then after integration, you take the limit epsilon to 0. And in fact, this is already used in out formalism, so it's explained in Peskin-Schroeder. Okay, you can compute this. And what you get is, well, you get something like this. Yeah, so the commutator of x1 mu at some position x and x1 mu at x prime, some Fourier integral. And if you go back to coordinate space, you get this. So you get something which is proportional to the metric. There is a sine function, so it depends which one is in the future and which one in the past. And it tells you it's only non-zero inside the light cone. This is zero. So what we have is we have a fully Lorentz invariant result. The commutator vanishes for space-like separations, and it's constant for time-like separations, but with a sign depending on whether you're in the future or the past light cone. So what is the interpretation of that? The interpretation is that, as I said, we need to describe our physics by new coordinates. So we take some physical point of our space-time, for example, the one where the sun is, something physical nice. In the background space-time, this is described by some background coordinates, small x. In the full theory, this is described by the coordinates capital X. So what this means is that the commutator is non-zero if the physical points where you look at are time-like separated. And then it's either plus or minus. So it's a very different kind of non-commutativity from saying just taking the x as operators on some Hilbert space. The x's themselves are not fundamental. The x's are associated to some physical point, which on the background spacetime is described by small x, and then the full thing by capital X. And these capital X do not commute. And so what we can get a Lorentz invariant result without being in contradiction to this earlier stuff. And there's a big amount of literature. A lot of people have thought about this. So it's a different kind, but it's something that comes very naturally from quantum gravity, if you think about it, as I said. Okay, and then if you look a bit more here, so as I said, the full coordinates are background plus first order correction. So if you plug this in, then you get, well, basically the same thing. So these things do not commute, told you before, but of course they're higher order corrections. There might be higher order corrections. And of course, the most general thing that you can have is that the commutator is some I times some matrix, operator valued matrix theta, depending on x and y. And this must be antisymmetric. So if you interchange x and y, and also interchange indices mu and nu, you must get a minus sign. And then in the usual approaches to non-commutative coordinates, or some well-known approach, like DFR, what you have is you take theta constant, not depending on x and y, and then you must get a minus sign when you switch indices. In our case, what we do is the indices are symmetric. We have the eta metric, the background Minkowski metric, eta mu, and the anti-symmetry comes from the sign function. It's a different result, but of course it's consistent. And then one can also look at, say, take the usual standard deviation formula for operators. The deviation of A multiplied deviation of B is greater than or equal 1/2 absolute value of the commutator. If you plug this commutator in, what you get is, well, we call it the generalized uncertainty principle, but you might disagree. So what we get is that the measurement of coordinates, so the uncertainty for measurements of coordinates x and y, is greater than or equal to Planck length squared, but only if you're inside the light cone. So if you measure x and y, one after the other, with a time-like separation, then they don't commute. Then you might have uncertainty. And then the standard deviation is exactly the Planck length. We didn't put anything, it really falls out. If you measure them with space-like separations, so say 2 different laboratories, then they can be exact. Okay, thank you very much. Here's my conclusion. Maybe I don't need to go through this in detail. While the basic conclusion is diffeomorphisms can be cured. They're an obstruction, but with all what I told you can be cured. You get some nice non-commutative spacetimes. And in the future, what we want to do is we want to go to higher orders in the Planck lengths to see if that simple formula is there or we get some other corrections. We also might want to look at different backgrounds. So we have a paper in preparation on the de Sitter background. And also we want to connect this to observations. And then if any one of you is interested in that, I think we would be very happy to collaborate. So these are the main references. Thank you very much.
We thank you a lot, Markus, for this inspiring talk. Anyone who would like to ask any question, you are free to just ask. I don't have to intervene. I mean, it's a bit like a dialogue.
Yes.
Please help yourself. Until someone asks a question, I would like to ask, you showed before something, a result about light geodesics, light cones with your collaborator from York.
Yes, okay. So, I have prepared a picture.
Actually, if you have time, you can talk about it. You said at the end. I think this is the time. Actually,
okay. So then, then let's do this. These are called geodesic light cone coordinates. So if you think about it, how do people actually make observations in cosmology? Well, using light. We point our telescopes at the sky, we look what comes in, and light travels along the light cone, quite obviously. So this is the light cone. Here we have the world line of some observer, W. This is us, this is the Earth. These are the light cones, back light cones. These are described by constant W, some coordinate. There's some event E happening somewhere, and then the signal reaches us along the light cone, so along this curve, this green curve here, at some fixed angle theta in the sky. And then, so k mu is the null vector of that photon that comes to us, and u mu would be the forward velocity of our observer. So there's some proper time of the observer sometime. This is a very nice picture. And so one can now say foliate space-time in that way. So there's a collection of observers which have their proper time tau, and all these look in the past. And yes, so let me maybe give the details. The vectors u and mu are geodesic vectors in that construction. And the hypersurfaces, as I said, of constant tau and w, they are n-2 spheres, so 2 spheres in 4 dimensions, which have parameterized by some angles, and these angles are orthogonal to the propagation of light. This is what we see in the sky. There's a nice quantity, which is the frequency of the photon, of the wave vector. So it's called upsilon or inverse upsilon. It's just the scalar product of k and u. And there's some other quantity u, which is, it's a misalignment of the photon propagation of that specific light cone. So, some other things. And then if you look on the background metric, so the background metric in these so-called GLC coordinates has this form. So there is this upsilon, this photon frequency enters here, and the other parts also enter the metric. And then on a cosmological background, what we have is that this frequency of the photon is just equal to the scale factor. So as the universe expands, photons redshift. So it's, the frequency is 1 over upsilon. So upsilon becomes greater as the universe expands. So that means that the photons redshift. 1 over upsilon becomes smaller. And the background metric is just, the background spherical metric is just a constant factor times metric on the unit sphere. And now if you add perturbations, one can construct invariant, or one can construct coordinates in that sense for these GLC constructions. And okay, what you do is you use the same conditions as before. So there's some perturbed proper time of the observer in that geometry. The perturbed forward velocity is just its derivative. Again, perturbation of k is the same. K is the gradient along the perturbed light cone. They are normalized and they are orthogonal to the angles, or the angles are orthogonal to that. And then what you get are corrections like these. So say, for example, if you look at that, that's maybe a nice one. So the first order correction to the coordinate w, from the background, it's really just constant. And the first order corrections to that w, it's an integral of your tau metric perturbation, rescaled, integrated along tau on the past, into the past. So it depends, if the coordinate that you as an observer see, depends on all the fluctuations of the metric in the past, very clearly. For the time coordinate, you have to integrate along the past light cone. So this formulation here gives you the past light cone in the background geometry, integrate the perturbation along that. So again, what you get is you get some non-local coordinates as before. So before, if you recall from the non-commutative coordinates from the flat space, we had the integral of the Green's function times the metric perturbation. So here the Green's function is some sort of one-dimensional Green's function along the light cone or the past time. And then one can define, as before, gauge-invariant relation observables. For example, invariant metric. So the gauge-invariant metric takes that form. It has the same GLC form, but now the upsilon gets corrected and also the other quantities get some corrections. And I said, yeah, one can look at the expressions. They are not so very nice. They become very long and ugly. So it's a very nice and physical coordinate system. Unfortunately, for computations, it's not very nice.
Quite hard, actually.
Yeah, you see, I mean, I had to make it smaller font just to fit on the thing. And so we'll also look at, say, the gauge-invariant Hubble rate. Again, it's some not so nice thing, but okay. So William and I are now supervising a master's student who is looking at correlations of this upsilon. So really,
In master level. Oh my God.
Yeah. It's a very good student. It's yeah. We plan to have a paper out beginning of next year. So I think it's very nice. So yeah, what we get is basically changes to the frequency of photons induced from graviton fluctuations. So this is directly related to the CMB, so what people see. So we expect to basically get the CMB spectrum directly from that. And I think that's a very nice thing. So, but yeah, unfortunately, I mean, originally we thought to compute the full correlation of the full invariant metric. So not only the upsilon, which is just one part, also this U and this gamma. But yeah, it got so complicated that we had to restrict the epsilon. Right. So yeah, so this is the construction.
Wonderful stuff. Actually, Fabio Scardilli would like to ask a question. Yes, Fabio, you're welcome.
Hello, Markus.
Hi, Fabio.
Hi.
Nice to meet you.
I have some questions.
Yes.
First, it would be correct to say that your observable coordinates are non-commutative, while on the contrary, the background nominal coordinates are commutative. So
yes.
the capital X, what you indicate with big X, the capital X or capital lecture are non-commutative coordinates. Are they observable, but they are not commutative? While on the contrary, if you have some nominal coordinates on the background, those are the standard
yes.
standard coordinates, so to say.
That's exactly correct. Yes.
Oh,
That's exactly what comes out. But of course, the capital X are the one that we actually need to describe the physics. So these are the true.
So the observables are actually non-commutative.
Yes.
I see.
Yes, absolutely.
And also, I have another question about the expression that you showed. I think I don't remember 5 or 6 slides ago about the correction to the Newtonian potential.
Yes.
You get 2 different terms. So one is 41/10. Yes, that one.
Yeah, exactly
that. Can you comment a little bit more on this? I mean, because the first term, 41/10 pi, is the term that usually is obtained by Donahue and collaborators, or people working also Krilipovich, other working in effective quantum field theory, right?
Yes.
If I remember well. And the second one, actually, I've seen in your works, in your papers, but I haven't seen that term in the papers of, for example, Donahue, in the last papers and last years. So, can you explain me a little bit more about that?
Of course.
The difference of these two terms.
Yes. So in the approach by Donahue or Krilipovich, I think, and collaborators, what they do is they look at the scattering of, say, scalar fields. So they take incoming scalar fields, and they look at all the graviton exchanges that you get, and then the scalar fields go out again, and they compute the S matrix element that corresponds to that situation. And then they look at the scattering from a classical potential and say the Newtonian potential is the corrected Newtonian potential is the one that gives you the same S matrix element as that computation with the scalar fields. So this is what I call inverse scattering method. And this gives this 41/10 pi. And this seems to be universal, so it doesn't matter whether you scatter scalar fields or you scatter fermions, you get always this 41/10 pi. And it is the same that we get here. So these are the contributions of 2 different classes of Feynman diagrams, if you look at them. This 41/10 pi, these are the Feynman diagrams with the graviton and ghost loops. And we get the same result, so this is very, very encouraging. And this term comes from Feynman diagrams, which have, so now I need to get back to the slide here, which have a Y running in the diagram. So, okay, let me explain it now a bit better. We have this point particle action, so that there's some heavy body of mass m, which we describe as a point particle, which has a position z. Notice that on the background, it's just a constant, so it stays at 0 and just moves in time, with a constant for velocity. And then it fluctuates a bit around that position, the heavy body. And okay, there's an m to the -1/2. And so the class of Feynman diagrams, which has these y's or propagators of these y's, of this fluctuating heavy body, this is what gives rise to this 43/12 pi. And so this is something that Donahue and Krilipovich could not consider because their method is just completely different. So this is something that people have not been looked at before. And I mean, it's no surprise that this term doesn't appear in their approach because it's a different approach. So here, what we're really looking at locally at some point in space-time, a heavy body and the vacuum polarizations of gravitons around that. And then they said there are 2 classes of Feynman diagrams, one which has the fluctuations of that body and one which has graviton loops. And the graviton loops give this one, and then we agree with that other method for the scattering of scalar particles, say. And this one, of course, I mean, this is completely new. This is something that no one has looked at before. So this is the relation.
I see. So you cannot get this 43/12 by these scattering methods. There is, I mean, they don't capture at all. No way.
They don't do that. No.
I see.
They don't do that.
I'm curious. Have you had some comment from Donahue or from people working
No, not at all. Not at all.
No?
No,
What,
no, no, no.
Have you tried to stimulate some comment? I don't know. Right?
Not yet.
What do you think
No,
about that?
No, not yet, not yet. Probably we should do that. Yeah.
Yeah. Let's try to see what. I mean,
What they say.
it's an interesting. For me, it's particularly interesting the fact that in any way the sum of the two, 41 over 10 and minus 43 over 12, is still positive.
Yes, that was also very surprising for us. Yeah, that's true.
Yeah.
So,
Okay.
it's what comes out. I mean, these are strange factors anyway, right? What is 41 or 43? This is not a nice number.
But the fact that it's positive is something because there was a certain bunch of years. I think in the papers of the first paper of Donahue 94, 95, and then in 2003, in which the coefficient that now you have with a plus in front of the 41 over 10, they got that coefficient with a minus and not with a plus.
Yes.
So and then I don't know, and maybe they summed the different kind of diagrams. I don't know what happened, but from 2003 to the very recent paper, the plus sign is coming back. So is still there.
Yeah. No. So there are many older papers which do not get all the Feynman diagrams that would contribute. And I mean, so I think the first correct one. So after Khryplovich and Kirillin had their paper, I think in 2003, then Donahue and collaborators had a paper which corrected the last mistake in their paper. And then Khryplovich and Kirillin had another paper in 2004, I think, which then also said, yeah, this is the correct value. And since then, I think it has been stuck. But before that, I think every paper is wrong, basically. So I forgot something old. So
the best paper are from 2003 to up.
Yeah. Okay. So that, I think that now everyone agrees that this is the correct thing. Yeah.
Okay.
Okay.
Thank you very much for the seminar and for your replies.
My pleasure.
Thank you very much for the contribution, Fabio. And Nicholas has left already. Thank you very much for the inspiring talk, Markus. And hopefully, since we are involved in a project, also we will see you next year in Kuwait for sure. 100%. So, we will talk on campus, and warm greetings to Germany from a hot Kuwait. It's still hot here, to be honest with you.
Okay.
What's the weather there?
Yeah.
And see you soon. Thank you very much for everyone who has participated. See you soon.
Thanks a lot for the invitation, and it was really a pleasure. See you soon. Bye.